Good morning. Welcome to the next Let's Calc video. This one will be the final video for the pure differentiation portion of the course this year. And this video is going to focus on what we're calling advanced differentiation. Basically, it's going to involve some more intricate chain rule work where you might have to do one or two, maybe even a third step of the chain rule within a problem. It's also going to involve functions that involve both chain, product rule, and quotient rule. Maybe all three, hopefully not, but maybe. And it'll just kind of bring differentiation into all the different pieces that we've looked at. We'll be using tables, we'll be using graphs, we'll be using graphing calculators, and we'll be bringing all that information together in a nice kind of culmination of what's there. Within this assignment, I'll let you know, since I just wrote it and did the written solutions last night, that there are some questions that I would consider very challenging. I'll try to let you know where they are. And I'm doing the vast majority of the questions on this assignment, just leaving out a few of the pure derivatives. But again, you have full written solutions for those as well. So without further ado, let's jump into the first problem, and let's start putting our differentiation skills to the test. Did it again. Alrighty, so this is the first problem of the assignment. It's a good place to begin. It's a very common function type that we'll run into. In fact, it has a name. In question number 1, we have the function 2x plus 1 to the 5th times 4x minus 5 to the 3rd. This is called a product of binomial powers because you are taking the product of two binomials raised to two powers. So basically our job is to take the derivative of this. Now in looking at it, it may not jump out at you right away, but this is going to involve two of our big three rules for differentiation. In particular, the first thing that I notice is I've got something to the 5th power times something to the 4x minus 5 to the 3rd power. So what I'm thinking is that this is going to involve, first and foremost, the product rule. In fact, I'm not just thinking it, I know it is. And then second, when we differentiate each of those individual products, you'll notice that the inside has a derivative that isn't just one. So that means it's going to be both the product rule, and it's going to involve the chain rule. And again, I'll let you know in the written solutions. I've done a lot of these assignments lately, so I'm getting a little bit burned out. So I didn't go through and do every single step as intricately as I might otherwise. I'll try to do that in the videos here and probably just come back to this one and do it over a couple hours. So in looking at this, the first thing I want to do is decide between those two rules which one comes first. Well, basically what you got to look at is what's the structure look like on the outside. And what I notice is I've got function times function on the outside. Doesn't matter that they both have something going on the inside and have compositions inherent to each. Just we've got two things being multiplied, so I'm going to start with the product rule. So in looking here, again, I'm going to be as intricate as I can. So the first thing I'm going to do is I'm going to have the derivative of the first prime times the second. And you can tell this can get a little bit complicated when you're working through it this slowly, just because primes and parentheses and stuff kind of clutter things up. Then we're going to have 2x plus 1 to the 5th times the second one to the differentiated. So there we go. So in looking at our ingredients here, what you can probably notice is that our hard work and heaviest lifting is going to be in differentiating these powers of binomials. So what I'm going to do is I'm just going to go and do a soliloquy on either side. Like until you feel ready to just differentiate as you're going, which again, I can definitely do this in my head. In fact, I'll do it right now. It's 10 quantity 2x plus 1 to the 4th. It's just, you can go faster once you get comfortable. But until then, you can just kind of think about it as, okay, now we've got a chain rule problem to work through. So in this case, I'm going to call them G. I mean, why not? Or actually, I'll call them B. Why not? So we're going to go B of x equals 2x plus 1 to the 5th. Again, these are pretty B for basic chain rule problems, so you could go faster. We might let b of u equal u to the 5th, and then we'd let u equal 2x plus 1. Naturally, that means b prime of u is going to be 5u to the 4th, and that means u prime is just going to be 2. That was just a linear portion. When we bring those pieces together to get b prime of x, hopefully you can do this in two steps. We're going to have 5u to the 4th. That u is 2x plus 1, and then u prime is going to be 2, which gives us, as I said earlier, 10 quantity 2x plus 1 to the 4th. So right over here in our problem, if we go to differentiate, we'll be able to bring that guy back in and call that star. Likewise, we can do an identical computation. Just I'm going to crunch this down a little bit to make sure I have room. Make that a little smaller this way. There we go. So to make sure we have enough room, let me do this one. So next we're going to look at, we'll call it b again. So we're going to let b of x equal 4x minus 5 to the 3rd. And by the way, if these extra steps are feeling kind of tedious to you, that's your motivation to get better at the chain rule and work through it faster. So in this case, we'll have u to the 3rd we'll have u equals 4x minus 5. b prime of u is going to be 3u squared. u prime is going to be 4. When we bring those pieces together and do it as a function of x, we're going to have 3u squared times 4, which ends up being 12 quantity 4x minus 5 to the third. It's about 3. And so there's the derivative over there that we did right here. So with that in mind, what does that do for us? Well, now it allows us to write out that next step. So watch me take that into action. So what this means is now f prime of x is going to be equal to the derivative of 2x plus 1 to the 5th, which we have right here. Granted, it's got an equal sign and a star next to it, but we can fix that. So we can bring in that piece. And notice I'm using the colors and literally dragging it over just to make clear where it's coming from. It'll still be multiplied by 4x minus 5 to the third. Then the next one we have 2x plus 1 to the 5th. And then multiplied times the derivative of 4x minus 5 to the third. And hey, look at that, we got that as well. And this one thankfully didn't drag the equal sign, so I can literally pull it out. So there's everything we need. Obviously this isn't perfect form, and more importantly, this can be factored. And in this particular case, for the product of binomial powers, I expect simplifying appropriately to equal factoring. I do expect you to factor for this one, and I have a good way to make sure you do it by placing it on the test in a multiple choice section, so you're forced to do it this way. So just keep in mind that's kind of where I'm thinking. So in here, what I want to do is I want to quickly calculate out and figure out what is the GCF for all of these pieces, because that's what's going to come out and leave us with the remainder. That will be the final factor of our derivative. So looking here, I'm going to look at 3 different pieces. First, I'm going to look at the numeric factors. I have 10 and 12. The GCF between them is 2. Next, I'll look at the 2x plus 1s. The GCF is always the smaller power. Even if it's negative, it's the one that's smaller. So 4 is smaller than 5, so we can pull out 4 2x plus 1s. And then finally, we have 4x minus 5 to the third and 4x minus 5. Oops, excuse me. That should have been to the second, shouldn't it? Where were you guys correcting me? Jiminy Christmas. Help me out a little bit here. Should have been 2. Probably because I was writing with bad handwriting. So with that said, we can look at that factor as well, now that we have it correct. And clearly the smaller power is 4x minus 5 to the second. So the reason we do that is it allows us to pull out the GCF, which as I said is exactly what we wrote a second ago. 4x minus 5 squared. And just for the record, because I'm going to be a little bit lazy here, I'm just going to write them out as a... I'm going to copy that GCF so we can use it again. As far as what's left over then, if we divide out a 2, we're going to have 5. If we divide out 2x plus 1 to the fourth, we're going to have nothing left there, just a 1. And then 4x minus 5 to the third over 4x minus 5 to the second is going to leave us just 4x minus 5 to the first. And in fact, you'll know you did this correct if we do in fact have a product of binomial powers, if you're left with the first power for each of those binomials once you factor. On the second hand, numerically we have 12, we pulled out 2, so that leaves us a 6. As far as the factors, we pull out 4x minus 5 to the second and 4 2x plus 1s. That leaves us with a single 2x plus 1. So there is the extra factor we're looking for to simplify things a little bit for us. Let's prepare for it. So of course our next line, which again you can be creative in writing around, just be careful. It's going to give us 20x minus 25 plus 12x plus 6. And as far as finishing that off, all we have to do is combine like terms, which is not the worst thing in the world. Looking at our ingredients, we have 20x plus 12x, which gives us 32x. And minus 19 plus 6 is minus 25 plus 6 is minus 19. Got ahead of myself. And there is our derivative. So again, this was product of binomial powers, a really common one. You notice my organization system was to take a little bit more time at the product rule and then soliloquy my way through the chain rule portions. But again, if you feel more comfortable going faster, more power to you. Ricky Bobby would be proud. Okay, next that brings us to question number 2. Question number 2 I think is an easier and simpler question than number 1. But the challenge here is that we've got 2 things going on once again. We've got a function times another function, and then that second function has something inside of it. So once again, we are looking at a product chain problem, or a product chain joint production. So we need to do both here. So once again, to start things off, because of that product and because I see two functions being multiplied before anything's on the inside, I'm going to start by setting up the product rule. So again, I'll do x cubed prime times secant of 3x squared plus x cubed times the secant of 3x squared prime. So in looking at our ingredients here, this one isn't quite as bad as the last one. This one's a little simpler. X cubed's derivative is just 3x squared. Didn't need any fancy rules to make that happen. But on the last portion, that secant of 3x squared, that's where the challenge really pops up here. This is where we have to do a little bit of work. So as with before, I'm going to pull this off to the side. I'm going to let f of x equal secant of x cubed, or 3x squared. Sorry, said that wrong. And then I'm going to decompose it using the chain rule, or to prepare for the chain rule. So in this case, secant's a little bit of a newer rule, so I could understand being a little less comfortable with it. But in any event, f of u would just be secant of u, and u is 3x squared. When we differentiate these pieces, the derivative of secant, think back, that's going to be all positive, because it's not a cofunction, and specifically secant u, tangent u. And then u prime is just 6x. When we bring these pieces together, hopefully you'll be okay sliding through one step. That's going to be 6x secant of u tangent of u. And u in this case was 3x squared. So there is our derivative. And of course it copies the whole thing. Tisk, tisk, tisk. Okay, so with that said, there is that last derivative that we needed. Now for this one, this isn't an inappropriate way to simplify your expression. I can't lie about that. I'd say this is okay. But of course, this can be cleaned up a little bit more. There's a lot of GCF in here. So to help me, I'm just going to first clean it by writing it in a more standard form with, monomials and things out in front. That's 3x squared times secant of 3x squared plus 6x cubed secant of 3x squared tangent of 3x squared. So in looking here, as far as GCFs go, I see that we can pull out a GCF of 3x squared as well as secant of a 3x squared. So when we do that, leaves us with one big factor remaining. I see a 1 only left from the first term because we factored out the GCF was the first term. Then the second one will have plus 2x, and we're left with only a tangent of 3x squared. And that, my friends, is our derivative. So once again, depending on your comfort with the chain rule and with some of the new reciprocal trig rules that we've gotten, your comfort may allow you to move through this problem way quicker than I just did, or it may require you to just be really organized and thoughtful as you work your way through. Either event, you're not wrong. You just make the goal of being a little more comfortable as you go forward each and every time. Oops, I was just looking and I realized I made a small mistake here. Something to correct, I'll do it in bright red. I have in here, by the way, I wrote down accidentally x squared when it was supposed to be x cubed. So let me correct that really fast. That should make this x cubed. That would mean that this power would not be 6x cubed, but 6x to the fourth. And since there's an x to the fourth and we're pulling out an x squared, that would mean our final answer would have a squared in it as well. So I apologize for the mistake. It wasn't too bad. It was nothing conceptually wrong, just a small little error as I worked my way through. But corrected now. So you're welcome. Okay, that brings us to question number 3. Question number 3 is a classic multiple chain rule problem. Now I gave it away a little bit. This is in fact a multi-chain rule problem. I used to call these chain rule superstar, just like those other ones. So in this case, before I do anything else, to kind of help us see this composition, we've talked about it before. This kind of strange older notation for trig functions raised to powers. Well, what I'm going to do is I'm just going to remind us that that is really 3 times the quantity cosine of 2x plus 1 to the 7th power. So that way we can clearly see that there's something inside. Inside of the 3 stuff to the 7th, there's a cosine of 2x plus 1, and inside the cosine, there's a 2x plus 1. So there are lots of ways to do this. I'm going to demonstrate it both the way that I formally teach it typically, as well as the way I would do it by hand myself. So in here, what I'm going to start with is I'm going to start making some composition work. So specifically, I'm going to first write out what h of u is. And that would have to be the most outside function here. So the most outside, I'm thinking, would be 3u to the 7th. And of course, ask yourself the question, can we differentiate that? Of course we can. In fact, I could do it right now. It's 21u to the 6th. Pretty easy. Next, I'm going to look at then what u is. Well, we can see that u should be cosine of 2x plus 1, but here's the thing. That expression requires the chain rule also. So instead of writing it as cosine of 2x plus 1, I'm going to write it as cosine of w. I'm going to make one final substitution of w equaling 2x plus 1. What this has done is we've done the quote-unquote double chain rule, because we've added a second substitution variable to go through to take care of the fact that our intermediate expression or function required the chain rule itself. So playing it careful from there, all we need to do is differentiate each one. It's the same chain rule, you just multiply all those pieces together. This becomes 21u to the 6th. U prime becomes negative sine of w, and w prime is equal to 2. Bringing those pieces together, we're going to get 21u to the 6th times negative sine of w times 2. So from here, this can be a little bit tougher. We have to go back through and back substitute a whole bunch of stuff. So being careful though, w it says is 2x plus 1, so that's not actually too bad. And then u it says is cosine of w, which in our case is going to be cosine of 2x plus 1. So that is our derivative for this thing that we've been looking for. In fact, I don't know why I did it over on the right side. Let's move it to the left. So that is our derivative. We just need to write it in a better form. So I've got the negative sign, I've got the 21 and the 2. It's going to give me a negative 42. We'll have cosine to the 6th of 2x plus 1. And we'll have sine of 2x plus 1. And of course, as with most trig functions, there's always other ways that you could write the expression. And there are a few. I see one involving a double angle expression that could be popped in here, as well as a couple others. But really, it doesn't matter how you approach it, as long as your final answer includes all those properties. And I will warn you that typically when this gets asked, this is a multiple choice type question, and it really gets to probe whether or not you understand how these pieces work and what are all the different inside parts. So typically what you'll see is you'll see a combination where people just go negative 42 sine to the 6th of 2x plus 1. They'll forget to do the intermediate step with the cosine. So make sure that, based on this warning, that you heed my advice and do what you should. Okay, the fourth problem we're going to look at is the only, I think, chain quotient or quotient chain combination that we have on this problem set. And I just wanted to do it just to make sure we go through the quotient rule once, because otherwise I feel like I sometimes ignore it. Excuse me, I am exhausted. Okay, the next problem we want to look at is going to be our only one that features the quotient rule and the chain rule. And I want to make sure that we covered one. I didn't want to completely forget about the chain rule. I want to make sure it was included as a part of this work as well. And of course, as I say this, I'm already stating that this is quotient rule, chain rule. I think the quotient rule is the easiest one for people to notice, simply because there's something divided by something. And the chain rule is specifically because of that 5x on the inside. So without further ado, let's attack this. And again, we're going to use the chain rule. So in here, my thoughts are, let's focus on using the song. Let's use the song to help recall what's there. Low, D high, minus high, D low. Yes, I know this derivative, but I'm just being careful and organized. All over, low, low quotient rule. Yeah, boy, I'm exhausted. Boy, I could fall asleep. Okay, so in here, we've got our work cut out for us a little bit. So as far as pieces that we need to work on, the x to the 5th is pretty easy. We are going to have to deal with the cotangent of 5x. We mentioned earlier that's going to be our chain rule portion. On this next one, we're going to have minus 5x to the 4th, cotangent of 5x. And all of this is going to be over x to the 10th. So already there's some good work that we could do here. We could clean out the x to the 5th and x to the 4th a little bit with some GCF stuff. But instead, as I've done each time here, this is all about bringing the chain rule in with the other rules we have. So I want to focus my attention on what we're going to call f of x equals cotangent of 5x. And again, I don't think this is a very difficult chain rule, but because it's involving the cotangent function, which is relatively new, it might feel more uncomfortable than it would otherwise. So let's start, like normal, with the 5x inside. We want to use the chain rule. So we're going to use the substitution method. The outside function, I think pretty clearly, is cotangent of u, because we've got something shoved into it. You can imagine this is cotangent of 5x. That means u would be 5x, which is nice. When we differentiate each piece, we do have to remember some rules. The derivative of 5x is much easier. It's just 5, because that's linear. The derivative of cotangent is just like the derivative of tangent, except opposite in every way. So tangent's derivative is positive secant squared. Cotangent's would be negative cosecant squared, and in this case of u. And then finally, when we bring the pieces together, the derivative is going to be negative cosecant squared of u, all times 5. Bring this all together, we get negative 5 cosecant squared of 5x. So with that said, we can go over to our expression here, and we can substitute it in. We're going to get negative, actually I'll just clean this up a little bit, negative 5x to the 5th cosecant squared of 5x. Actually, I'm not going to use parentheses, sorry. Minus 5x to the 4th cotangent of 5x, all over x to the 10th. So that is our derivative. That is actually a fully acceptable answer. It just could be cleaned up a little bit. I mean, I hope you can forgive me for that. So in looking here, there's a bunch of stuff I want to do. I want to pull out GCFs again. Seems to be a common simplification technique. What I notice is that we can pull out a negative 5x to the 4th. That'll leave us with, in our numerator, x cosecant squared of 5x, and then plus cotangent of 5x. And then in our denominator, which I'm going to shift over to the side, we get x to the 10th left over. So of course, with x to the 4th over x to the 10th, we can divide those pieces out. So let's get a different color here for a second. We can divide that, and this will leave us with 6 x's in the denominator. To wrap all this stuff up, we can write it almost exactly as we see it. Negative 5 over x to the 6th, x cosecant squared of 5x, plus cotangent of 5x. And there is the derivative that we were looking for. We combined the quotient rule and chain rule. We were careful. We did another one of those little soliloquies over here to make sure we could do the chain rule portion. And we finished it out with the correct answer. Okay. Our next problem that we're going to attack is question number 7. And question number 7 is what some people might derogatorily call a trick question, because in actuality this requires almost no work, but it does require some significant knowledge. If not, this just becomes a challenging, like, multiple step chain rule problem. So let me point something out before we begin. This is what I did in the written solutions, and I did it the other way too, just like I will here. What I'm going to point out to you is I'm going to remind you about a specific trig identity. And it's something that's pretty interesting. So let's remind you with a particular right triangle. In particular, I'm going to choose a 3, 4, 5 right triangle. We'll call that angle theta. So first I might ask you, what is the sine of theta? And you'd say 4 over 5. Then I might ask you, what is the cosine of theta? And you'd say 3 over 5. And then I might ask you, well, what happens if you get and square sine, and then square cosine, and add those two things together? Well, in this case, you're going to get 4/5 squared, which is 16 over 25, plus 3/5 squared, which is 9 over 25, which equals 25 over 25, which equals 1. So interestingly enough, you might argue, well, in that case, sine squared plus cosine squared equals 1. No, it's not true at all. Always, for any angle, sine squared theta plus cosine squared theta is going to be equal to 1. And each of those are defined for all real numbers. So this is always true. This is a trig identity. In fact, it's called the Pythagorean identity. So with that in mind, what you can know is something that's also kind of small. Maybe it didn't come up last year, but it's worth pointing out here. And that is, even though this is sine squared of theta and cosine squared of theta, as long as those two things are the same, it doesn't really matter what they are. It could be sine squared of anything plus cosine squared of that same anything, and it'll still be equal to 1. So over here, we have sine squared of x squared plus cosine squared of x squared. That is literally equal to 1. And if h of x is equal to 1, then h prime of x is equal to 0, because this is just a constant. So in reality, this is just a trick question to see whether or not you recognize a particular trig identity. If you do, congratulations, it's the easiest problem on the assignment by a good margin. If you don't, yeah, good luck with that. So now, of course, you're not going to all recognize that, and even if you do, even if you think it might be true, you might not trust it, which I can understand. I get it. So instead, let me point out what this would look like if you decided not to do it that way. So this is the person who, this is Sisyphus' way of doing it, where you're just going to keep grinding through difficult things over and over again. So let me point out that h of x is equivalent to sine of x squared, all squared, plus cosine of x squared, squared. So take that for a second. Let's do each of these derivatives off to the side. Again, let's just play it safe. Each one's going to require the chain rule, of course, but let's play along. So if we want to let's go f of x equals sine of x squared squared. I would let f of u be u squared. I'd let u equal sine of, well, it's supposed to be x squared, but I'm going to let it be another thing, so sine of w. Then I'd let w equal x squared. Taking the derivatives, f prime of u is clearly 2u, u prime is cosine of w, and w prime is 2x. Bringing all that together, we're going to end up with 2 sine of w, and you can see sine of w is u, so w is x squared, so I'm just going to punch it in. 2 sine of w times u prime, which is cosine of w, also known as cosine of x squared, and then times w, which is 2x. In other words, for this one, you get 4x sine of x squared cosine of x squared. So with that in mind, I can go over here in my h prime of x calculation, which I'm going to have to fix the colors for. I'll deal with this in a second, and I'll do it right now. Should have been better prepared, I apologize. So h prime of x is going to first be equal to, we've got 4x sine of x squared cosine of x squared. Okay, that was our first part. Next, we want to look at what the derivative is for cosine of x squared squared. So doing this, we'll follow the same exact pattern. We'll do f of x is equal to cosine of x squared squared. So f of u is u squared. U is cosine of w this time, so it did change. And w is x squared. Now some of this doesn't change. F prime of u is still 2u. U prime is now negative sine of w. And w prime is still 2x. Bring this all together. We're going to have 2u, which is going to be 2 cosine of w, times u prime, which is negative sine of w, times w prime, which is 2x. And pulling that all together, we get negative 4x cosine of x squared sine of x squared. So over here, what we're going to be adding to it, let's see if the computer likes me. It does not. Of course not. Ignore this for a second. Boom. What we're going to be able to pull over here is the derivative that we're looking for. Oh, come on, really? So when you don't feel good, the computer does not want to cooperate, does it? In any event, voila. There's the derivative of cosine of x squared squared. Now here's the interesting thing. You probably can see it already. 4x sine of x squared cosine of x squared plus negative 4x cosine of x squared sine of x squared is 0. So whether you want to do it the hard way or the easy way, you get 0. This function we have, h of x, is a very bizarre looking constant function. So its derivative is, of course, 0. Go figure, challenge for sure, but I thought it was just kind of an interesting question to ask. So showed you 2 different ways to approach it. Enjoy. That next brings us to question number 9. Question number 9 is the first of 3 free response style questions that involve lots of tricky, twisty derivative work. I think these are all good preparation, although one of them I consider to be an extreme challenge, so we'll talk about it when it gets there. For the moment, though, question number 9 is the only one of the 3 that doesn't require a calculator, so I'm going to do that, then I'm going to eat lunch, because I feel like I'm going to collapse here. So, in question number 9, it states that the piecewise linear function L of x is graphed at right. So, this is L of x. We're looking at the graph of L of x, and it is definitely piecewise linear, because it looks like there's just 3 different lines, or 2 lines, 2 rays, and 1 segment, whatever. Then it says let f of x equal that 6 over x minus x squared. So we've got 2 different types of functions to look at, one algebraic, one graphical. The first question, question A, asks us for what x values is L of x non-differentiable. So if you'll recall, a function that is non-differentiable has one of 3 different possibilities. The first possibility for a place where L of x might be non-differentiable would be a place where L of x has a discontinuity. looking at our graph, is there any discontinuity? Any place where the graph either has a jump, a vertical asymptote, or a hole? The answer is no. It looks perfectly well defined and nice and continuous. So there is not any discontinuous point on the graph of L of x. So that can't be it. So that one's out. The second option would be a vertical tangent. So that would be a place where the slope goes to infinity, not the graph, but the slope itself. It'd be a place where we have something maybe asymptotic or something cube rooty. We'd be looking for something like that. And the answer to that, since we have 3 lines, is also no. There's definitely no vertical tangent here. Like all of these are lines with nice finite slope. So no vertical tangent. So far, 2 out of the 3 possibilities not there. That last possibility, though, is what I prefer to call a sharp turn. You might know it by another name, a cusp, a curve, pointy point, whatever, corner. So for sharp turns, that's anywhere where the slope abruptly changes from one value to the other, because the derivative of the function is discontinuous, but the function is continuous. The answer here is, yeah, there are 2 places where if you put your eye on it, it would absolutely poke out your eyeball. One is right there, one is right there. So my answer to this question is, are there, for what x values is L of x non-differentiable? It'd be at each of the 2 sharp turns. Yes, at x equals, it looks like -1 and x equals 3. L of x has sharp turns. I should say has a sharp turn. I think grammatically that's correct. So throwing it in there, we can see just from visually looking at this picture, in this graph, we can see that we can see that there are in fact 2 places where the function is non-differentiable. Okay, question 9b starts by stating that we're going to let c of x, maybe c for chain rule, equal L of f of x. So we're plugging the algebraic function into the piecewise linear function. So keep that in mind. They want us to then compute c prime of 1. So since we're talking about c prime, I'm just going to go ahead and start by calculating out what c prime is equal to. So we want to figure out what c prime is equal to. In this case, I see a function inside of another function. That makes me think of the chain rule. And so in here again, I wouldn't do this necessarily if I was doing it for real, but we'll go ahead and do it as formally as possible. So if we want to do this as c of u, we'd probably go L of u. And then the inside u would be equal to f of x. That means c prime of u would be L prime of u. So it'd be the slope, whatever slope of whatever section we're looking at. U prime would be f prime of x. And bringing these pieces back together, we can state that c prime of x is equal to L prime of u, and u is f of x, times f prime of x. So there is the derivative that we're looking for. Pretty much a standard chain rule, but again, we're playing along. In particular, in this case, we want to figure out c prime of 1, and that's going to be L prime of f of 1 times f prime of 1. So with that in place, let's go find a couple of these values. That's what it's going to take to evaluate this. I'm going to start with f prime of 1. Okay, so like I said, f prime of 1. So, well, we haven't calculated the derivative of f of x yet, so let's do that really quickly. So f of x is known as 6 over x, or 6x to the negative 1, minus x squared. That means f prime of x should be negative 6x to the negative 2, minus 2x, or negative 6 over x squared, minus 2x. If we want to figure out what f prime of 1 is equal to then, we'll just plug in 1. We'll get negative 6 over 1 squared, minus 2x. Or sorry, minus 2 times 1, which is negative 6 minus 2, or negative 8. So we know right now that f prime of 1 is equal to negative 8. Our next move we want to hit is we want to start to attack the first factor in here. So we want to figure out what's being plugged into L prime. So f of 1 is going to be our next calculation. Well, that's not going to be hard. We have it right here. If we know f of x, f of 1 is just 6 over 1 minus 1 squared, which is 6 minus 1, or 5. So we're going to be plugging 5 into the function, or into the derivative of L. So basically, there is our value of c prime of 1. All that remains is we just need to figure out then what is the derivative of L at 5. So looking over at our picture, as I look up here, we got some frou-frou already on there, excuse me. What I want to do is I want to figure out what the slope is right at this point, but I realize that that's an entire line, and so the line has the same slope everywhere. So let's count out the slope from here. 1, 2, 3, 4 up, and 1 over. Tells me that the slope at that point is 4. And since the slope on this entire line is 4, that means L prime of x equals 4 right there as well, and specifically L prime of 5 equals 4. So given that, we'll get that C prime of 1 is equal to 4 times negative 8, and that simplifies nicely into negative 32. So C prime of 1 is equal to negative 32. Okay, question 9c. Compute the average rate of change of L of x for negative 2 less than x less than or equal to 5. So again, you might be predicting that this is going to be a particularly difficult one, but in light of what we've done before, we actually have a good amount of information, and I took pity on you and gave you nice points on the graph. So in looking here, of course, if we want the average rate of change of L of x, we don't have to think too hard. That's just the difference quotient, or the slope, point slope formula. So this is L of 5 minus L of negative 2, all over 5 minus negative 2. And although the numerator will take a little bit of work, that denominator is going to be 5 plus 2, which is going to be equal to 7. From here, we need L of 5 and L of negative 2. So L of 5 we just found in the previous problem. In fact, we stated on that last one that L of 5 is equal to 4, so that was easy. L of negative 2 is right here. Looks like that is 1. So we get 4 minus 1 over 5 plus 2, which is 3 over 7, which is an obnoxiously long fraction bar, also known as a vinculum, I believe. In any event, our average rate of change is 3/7. And you're welcome for one simple problem to work through. Okay, finally, that brings us to question 9d, which asks us to evaluate a limit as x approaches infinity. And in this case, we're looking at the limit as x approaches infinity of f of x over x ln of x. So, a couple things to look at here. First, before we do anything else, f of x is given nicely to us. So I'm just going to go ahead and punch it into the expression, make it a little easier for us to handle this thing. Our denominator, though, that xl of x is where we got to focus our attention. So now we want everything to happen here. We're interested in L of x as x goes to infinity. And what that tells me is I need to figure out what's going on with the function over here. So specifically what I see is that ray is defined as L of x for all x values greater than 3. So for x greater than 3, L of x is the line. And here we just need to figure out the equation of this line. It looks kind of gross, but whatever. I want to figure out the line. So in here what I'm going to do is I'm going to first take into account the slope. We calculated the slope earlier, said it was up 4 over 1, which means the line is going to be y minus something equals 4x minus something. And in looking at our ingredients here, I'm going to choose as my point on the graph, I'm going to choose the one right down here. That's going to be 3 comma negative 4. So putting it in, that's our line. That's going to represent L of x. Simplifying things, that's going to be y plus 4 equals 4x minus 12. And if I subtract 4 from both sides, we're going to get y equals 4x minus 16. So what we just found out is L of x is the line, y equals 4x minus 16. All that stuff below is just to work when x is greater than 3. And in other words, as x approaches infinity, L of x is 4x minus 16. So that means we can take our limit and we can rewrite it even better now. We'll do the limit as x goes to infinity of 6 over x minus x squared, all over x quantity 4x minus 16. And simplifying things just a little bit here, let me just erase this for clarity's sake. We're going to get the limit as x goes to infinity of 6 over x minus x squared, all over 4x squared minus 16x. Now our next move is to actually evaluate this limit now that we've got everything in place. And at first as you look at it, you might be tempted to just plug in infinity, but unfortunately if you do, you end up getting negative infinity over infinity, which is not ideal. So for now, what we're going to do instead is we're going to treat this and approach this using the formal attacking technique for limits at infinity. So what I want to do is I want to find the highest degree in the numerator and the denominator, either one. So looking in the numerator, we have x to the second versus x to the negative 1, and down below we have x to the second versus x to the positive 1. The largest degree here is x squared, so what I'm going to do is I'm going to multiply both the numerator and denominator by 1 over x squared. When I do, and distribute it in, of course, that's going to give me the limit as x approaches infinity of 6 over x cubed minus 1 over 4 minus 16 over x. And at this point now that we've taken care of things, we've got it in an algebraic position we can evaluate. We're going to direct sub. We'll get 6 over infinity cubed, which is 6 over infinity, minus 1, over 4 minus 16 over infinity. Well, of course, we've said this before, but a finite value divided by infinity approaches 0, or goes to 0. So this is really 0 minus 1 over 4 minus 0, and I hope you'll trust me when I say this is negative 1/4. Voila. There is our answer to 9D. Haven't done this for a little while, so I thought like it was a good thing to toss in there for you and keep active in your mind. So that brings us to question number 10, the first of the two free response style calculator enabled questions, or calculator active questions. So you'll be using graphing calculators on parts of questions 10 and 11, but 10 itself is focused a little bit more than number 11, which kind of goes crazy off the board. So let's focus in on number 10 though first. So in question number 10, again with calculators active, it says 2 rodents, a mouse, and a gopher are traveling along the x-axis. Again, must be a pretty wide x-axis. The mouse's position at time t is given by m of t, and it looks like we got a function in there with t squared sine of t minus the square root of t plus 4, so it's all stuff we can differentiate, good to know. While the gopher's velocity is given by g of t equals stuff. So basically a good place to begin here, as we're just reading, not even looking at what we're looking for here, is to point out if we're talking about position. So here, in fact, let's do this. I'm just going to make a little table here. I think this might help us a little. So for position, we've got to deal with the mouse. We've got to deal with the gopher. So as far as what they've given us, they're telling us the mouse's position is given by m of t. The gopher's position we don't know anything about. So we're given nothing in the problem about the mouse's or the gopher's position. For velocity, if we want to find that, they tell us the gopher's is g of t, something that looks like we'll need our calculator to deal with. And then for the mouse, if we want to find the velocity, we need to take the derivative of the position function. So we could go from there. And then last but not least, unless we're asked somehow about jerk, for acceleration, we'd need to compute the derivative of m prime, also known as m double prime. And for the gopher, it would just be g prime of t. So it's kind of an awkward situation because we're starting in different spots. One's beginning with position, the other one is beginning with velocity. But keep in mind, we got a calculator, so that should help us, and these questions should be designed so we can attack them. So let's start with 10a. 10a says, find the mouse's velocity function. So we want that mouse velocity function, which in our little organizational tool over here is going to be m prime of t. So if we want m prime of t, that means we're going to need to differentiate with respect to t, that m of t function, t squared sine of t minus root t plus 4. And notice it's not asking at a specific point, it just wants the function. So this is something we can't use our calculator for. We just have to use differentiation skills. Well, in looking at the pieces here, some of this is going to be a little harder than others. Obviously, that first term, t squared sine of t, is going to require a little bit of work, so I'll postpone it for a second. Then we're going to subtract the derivative of square root of t, which is just 1 over 2 root t. And then the derivative of 4 is 0. So really, our focal point here is going to be in figuring out what is the derivative of t squared sine of t. Well, it shouldn't be too bad. That looks like t squared times sine of t, so I'm thinking that we're going to use the product rule. And I can do that really quickly here. The derivative will be the derivative of t squared times sine of t plus t squared times the derivative of sine of t. So simplifying all those pieces, we're going to get 2t sine of t plus t squared cosine of t. And then to complete the rest of this thing, we can just bring down the rest of this derivative, which in our case is just 1 over 2 square root of t. And that is m prime of t. You might even want to call it like v sub m or something. But there is the velocity function for our mouse. Now, before I run forward, since we've got other questions coming up involving the calculator, I'm going to go ahead and take advantage here, and I'm going to put in all the functions that we have, even before we jump into part B. So in particular, let's jump in here. We got old functions in place. So what I want to do is first, since we don't know anything about the gopher's position, I'm going to put in the velocity functions in here. So for the mouse, I'm going to call that y1. That's 2x times sine of x plus x squared times cosine of x. And then it's minus, and then I'm going to use the fraction button because why not, we're here. 1 over 2 square root of x. Okay, so there is y1. Again, that's going to be our mouse's velocity. And then for y2, I'm going to let that be the gopher's velocity, which is 3 to the cosine of x. And again, keep in mind we're letting x play the role of t. And then times the square root of ln of t plus 1. Okay, so there are two. So keep in mind what we've just done is we've just input into our calculator. We have this as y1, and this is y2. So again, that's just kind of preparing us for the work that's about to come. Okay. The next question, 10b, asks us to find the acceleration of the gopher at time t equals 6. Well, for our sake, I'm going to go ahead and just copy this and steal it and bring it along. It is my name after all. I suppose it's fair that I steal something here, especially when I made it. Yeah. So we want to find the acceleration of the gopher. So looking over there at the relationship that we have, the acceleration of the gopher, it says, is just going to be g prime of t. So we have up there that g of t is this complicated expression, but we don't have the ability to differentiate that. We don't know how to do numbers to a power, a functional power, and we don't know how to do natural logs. Not to mention that this would be really hard even if we did. I do. You will learn it eventually. Just for now, we don't. So what we need to realize is if we want the acceleration, that means that we are looking for a particular value of g prime. In particular, we want to know what is g prime of 6. Well, g prime of 6 can come right out of our calculator. Our calculator can compute that, so why not? So we want g prime of 6. Recall, we said the gopher was y2. So if we go in here, we can go math 8. You could also graph it, of course, but I'm just not going to. Go math 8. For our function, we're going to put alpha trace y2. And then we're going to ask it to calculate at t equals 6. And pressing enter, we've got our answer, 1.377. Or you could also truncate as 1.376. So there is our acceleration. All we needed was to realize that that was going to be the derivative of the velocity for the gopher. And again, we'd already organized all that information in part A. So we got to our answer really fast using our calculator's differentiation feature, math 8. Okay, the third piece, which once again I'm going to take advantage of copying and pasting and bring over that little organizational work we had before. Keep in mind I wouldn't need this if we were doing it all on a single page, but I'm trying to organize better. So the next question, 10c, asks us for what times 0 to 4 did both rodents have the same velocity? So same velocity is code for equal velocities. And now I realize that what you might be thinking is, well, let's just go look at where m prime and g intersect. And that's absolutely right. But we can't actually report these answers without explaining what it was that we were doing in our calculator. We need a bit of context here. So what we want is we want an equation that demonstrates same velocity. So in our case, what that would mean, and we don't even need to say this part, I'm just writing it here for the sake of clarity. Same velocity implies m prime of t, that derivative we found earlier, is equal to g of t. And then what we're going to seek is we're going to seek intersection. We're going to try to figure out wherever they cross one another, because that would be our solution. So digging in here, we already have them in as y1 and y2 respectively. We talked about that earlier. I want to now graph these guys and find where they intersect, but I specifically want to see it on the interval from 0 to 4. So I'm going to go into my window. I'm going to go from literally 0 to 4. And then for y values, I'm not sure what's going to be there, so I'll just go with what they got. And then I'm going to graph. Graph's so much faster on here. Okay. So what it's looking to me like is it's looking to me here. Let me do this. It's easier if we just have this here. If you've never used the snip tool before, you are missing out, my friends. Okay, so there's where we're going. It looks like these were the two velocities. I believe the red was the mouse. And this would be m prime. The blue would be g. We're looking for anywhere where they have the same velocity. That occurs twice, it looks like, both times when they have a positive velocity. So our job is to now actually find the intersection. So in looking over here, let's see what we got. So second trace, we want intersection, which is option 5. I'll do enter, enter. And it looks to me like the first one is over there at t equals 1. So we get 0.948. And I'll point out that also you could have truncated to 947. So that gets us the first value. That was this one. To find the second one, we repeat the exact same process. Second trace, we'll go option 5. We're going to do enter, enter, and then I'm going to guess it's about 2. Let's see if that does a good job. It does. 2.172. Or you could do 2.171 truncated. So there it is. Again, our tool here was finding intersection. And of course, the essential piece, the piece that you would lose points for on an AP exam or on a test that I give you, is communicating this line, that this is the equation you're solving and getting these values from. Otherwise, it just looks like you looked over your shoulder and found someone else's paper that looked promising. So make sure that piece is in there, and you'll be good to go. Okay, finally, question 10D. And I will admit to you, dang it, I lost my fun thing from before. Let's go grab it. So I will admit that 10D, I've never asked this early in the course before, but I think it's a question that you have the ability to answer at this point. So I think that it's fair to ask this question. Excuse me. At time t equals pi, the gopher is at x equals 13. Okay, so we know something now. We know what the gopher's position is at 13. The question is, are the two rodents moving toward or away from each other? And I assume that should be at t equals pi. So we'll make sure that that's in there. Let's write that in right now. At t equals pi. So show all the work that leads to your answer. Okay, so first, before we do anything else, it's hard to communicate this when you're doing written solutions. So let's just illustrate what we're looking at here. So we've got two animals. We've got a mouse. Let's draw these things. And I'm good. I've watched Ratatouille. There's our mouse. Great mouse, right? So we've got a mouse, and it's traveling along the x-axis. At this moment, it's somewhere. It could be going this way. It could be reversed and going the other direction. We don't know for sure. Second, we have a gopher. Looks like a cat. Maybe I'll make those the eyes. It's like a platypus with an overbite. I don't know. Okay, I'm just not good at this. Let's do this. We've got a mouse. And we have a gopher. They are somewhere on this x-axis. So this is the x-axis. So what we need to do is we want to figure out if they're moving toward or away from each other at this time t equals pi. So the idea would be, if g is here and m is here, then if g has a negative velocity and m has a positive velocity, they're moving away from each other. Whereas if g has a positive velocity and m has a negative velocity, they're moving towards each other. Likewise, if we reverse those two pieces, we put the gopher over here and the mouse over here, then we would also be able to tell the same thing by looking whether or not they're signs, or which one was which and which sign was going where. So what we need to do basically is we need to figure out two things. We need to figure out each animal's position at t equals pi. That's an essential first step. And second, we need to figure out each animal's velocity at t equals pi. Not because we're actually that interested in how fast they're moving, but specifically because we're interested in which direction that sign of the velocity will point them in, because going left or right could mean a lot of different things. So in here, we've got to do two basic things. So I'm going to use a different color for each one. So I'm going to start with green to figure out the position. So we want to figure out where on the x-axis each one of these things are, or is. So for position, let's look. Well, at t equals pi, they told us that the gopher, I should do this as well, mouse and gopher, they told us that the gopher is at x equals 13. So we know that for sure. The question is, what about the mouse? Well, it says the position of the mouse, or in our table, it says is m of t. So we want to calculate out what m of pi is. So looking at our equation, that's going to be pi squared sine of pi minus the square root of pi plus 4. So for our purposes, that's not very helpful. So we would probably go to our calculator and ask what that value is. So pi squared, oops, I don't want to do it there. Pi squared times the sine of pi, oh, that's 0. I just realized. Oh well, my apologies. Minus the square root of pi, all plus 4, tells us that the position of the mouse is 2.278. And 228, I think. 2.228? Yeah, it won't matter, but there it is. So the gopher is at 13, the mouse is at 2.28. So that means right here on our mouse, we could go ahead and label this as 2.228. And over here on the gopher, we could label this as 13. So we know for sure that the gopher is to the right of the mouse. So now it's just a matter of checking the signs of their velocities. So for the second thing, we're going to look at the velocities of each animal. How fast they're moving, and built in, what direction. So in looking here, we're going to do the same setup as before. We're going to look at the mouse's velocity, and we're going to look at the gopher's velocity. Well, for mouse, we said velocity is going to be m prime of t. So we're interested in what is m prime of pi. Well, our graphing calculator can calculate that for us. Remember, we put in m prime as y1. So if we want to figure out what y1 of pi is equal to, we can, of course, do alpha trace y1 parentheses, pi. And it tells us that the velocity of the mouse is negative 10.152. So we now know right off the bat from that information that the mouse is moving to the left. So my expectation at this point is that the gopher must have positive velocity so that we'll be able to work our way through and answer this question accurately. But of course, how do we find the gopher's velocity? Well, we said earlier that the gopher's velocity is what they told us it was. It's that g of t function. So in other words, we want to calculate g of pi. Well, once again, our graphing calculator has that ready to go. G of pi is just y2. I mean, look at it. There it is. y2, 3 to the cosine of x. So to do this, we just want to once again do alpha trace. This time we'll do y2 of pi. And it tells us that the velocity there is very small, but positive. So with that in mind, to draw our conclusion, what we just showed was that the velocity of the gopher is small, but positive, meaning the gopher is moving to the right and the mouse is moving to the left. Based on all this information, there's nothing you really have to state, although there are ways you could state it. But what we've just shown is because the mouse is to the left of the gopher, and the gopher and mouse are moving in opposite directions, we can say that they are rodents are moving, and you want to say away from each other. I don't want anyone to say the rodents are moving away, because that could just be like a Fievel story where one's going west and traveling and moving away from home. So we want to be specific here. We want to say that they are moving away from each other, or moving apart would be acceptable as well. But again, as far as the show all the work leading to the answer, this and this, that's all the work that we're supposed to show. So with that in place, very advanced and somewhat challenging question, but we have all the ingredients we're looking for, and we've determined some information about these two creatures. And as a heads up, later on, you'll actually be able to find the position function, or be able to represent the position function of the gopher. For now, that's something that's missing, but we never actually needed it, because you had just the right amount of information to answer that question. Alrighty, this brings us to the final question, although it contains 4 meaty questions in here. Question number 11, also a calculator active question, although I forgot to put the label in there. And in this case, you're going to be again dealing with 2 different functions. In this case, though, one is provided through a table and presented numerically. The other one is provided as an algebraic function, but unfortunately it's one that we don't have the ability to differentiate just yet. So basically, we're going to have to combine our calculator skills with our numeric analysis skills and evaluate some things and find some stuff. So personally, I will tell you right now that I wrote this question as one of the more challenging questions to do. Like, I found it challenging and interesting for sure, but definitely challenging to try to work through and balance the need to use your calculator as well as look at everything on there. Not every part's created equal. I think it's C is probably the most challenging part if memory serves, or B, I think. No, C. C is the challenging part. But know that this is a good setup and good preparation. If you can work your way through this, I think you've really mastered a lot of the stuff in this unit. So without further ado, let's jump into question A. So in 11a, so first of all, in 11 we mentioned that we've got a g of x function presented numerically, h of x algebraically. Again, we'll need to use our calculator for it. In fact, before we even start, let's just go ahead and get that out of the way. So I'm going to go ahead and punch it in. We already did all the work on the last problem. So let's put in h of x is going to be ln of 2 to the negative x plus pi minus 3 sine of x, I think. Minus 3 sine of x, yes. Okay, so there it is. So we now know h of x is y1. So just kind of keep that in the back of your mind, y1. So from here, it says first, let p of x equal g of x squared plus 1, h of x. Write the equation of the tangent line to p of x at x equals 2. So we want a tangent line. Hey, haven't done that in a little while. It's a good thing to pull in there. So in order to get the tangent line, of course, we need two things. We're going to need to figure out, first and foremost, p of 2. And then second, the part that's going to involve some heavy-duty calculus, we're going to need to figure out what p prime of 2 is. So we're going to need to pull all that information together. Let's start with the cleanest bit. Let's figure out what p of 2 is equal to. So looking at our ingredients, p of 2 is going to be g of 2 squared plus 1 times h of 2. And that's going to be g of 5 times h of 2. Looking at our table, g of 5, we do know. G of 5 is 3. So that's 3h of 2. And then for h of 2, yeah, we could plug it in up here and get an exact value, but instead I'm just going to let my calculator figure it out for me. So g of 5 times h of 2, pulling in our graphing calculator, it's going to be 3 times h of 2. And remember, we said that since y1 is h in our case, we can go ahead and just use alpha trace y1 and put the parentheses of 2. And this should give us our value. It looks like we get as our y value negative 1.22977,343. So negative 1.227. Let's make sure I get all the decimals here. 977. Did I do that right? 22977,343. 7. And you know what? We don't need that many decimal places, so there it is. So there's our y1. So in a sense, we can't call it y1 because we have the functions. But whatever. There it is. There's our y1. So there's p of 2. Our next move is going to be to figure out p prime. Before we can figure out p prime of 2, though, we need to figure out what p prime of x is equal to. So looking up there, we need to take the derivative of this expression. And I can already tell you right now, this is going to require two different rules. First, it'll require the product rule, because we're multiplying g of something times h. And then second, we're also going to require the chain rule, because of the fact that we've got x squared plus 1 inside the function. So setting this up to be as careful as possible, we're going to have first the derivative of g of x squared plus 1 times h of x. And then we'll have plus g of x squared plus 1 times h prime of x. That part's easy enough. We need the derivative of h. There it is. So as far as ingredients here, most of this isn't going to be terrible. We have a graphing calculator for it. The biggest thing for us to deal with here is going to be the g of x squared plus 1. It's a little harder to see. I clicked the wrong green. There we go. So the question is, what is the derivative if we have g of x squared plus 1? So I'm going to go ahead and off to the side, do another soliloquy. I'm going to call f of x g of x squared plus 1. We want its derivative. I would hope that you could do this a little bit faster, but for now we're fine. So I'm going to let f of u be g of u. And then I'm going to let u be x squared plus 1. F prime of u is going to be g prime of u. And u prime is going to be 2x. Bringing all that together, excuse me, f prime of x is going to be 2x g prime of x squared plus 1. So with that in place, p prime is going to be 2x as we said, g prime of x squared plus 1. Then the rest of our derivative can pop in cleanly. We'll have h of x plus g of x squared plus 1 times h prime of x. So that is p prime of x. We've done all the work. We've done the chain rule and the product rule both. Now it's time for us to calculate p prime of 2 specifically. So that'll be 2 times 2. G prime of 2 squared plus 1 is 5 times h of 2 plus g of 5 times h prime of 2. So now as far as values, simplifying as much as we can, we have 4. G prime of 5 is 11. So that's going to be 4 times 11 h of 2. Then we'll have g of 5 is 3 times h prime of 2. So in order to do this, we're again going to need to use our calculator. So we don't have everything ready. This was 3h of 2, not h prime. So in order to do this, I'm going to need to pull my calculator into the problem one more time. So for the moment, I'm going to set aside the 44, or the 4 and 11. I'm just going to look at h of 2. So first of all, h of 2, I'm going to again be clever here. I want to save myself a little bit of time. H of 2 is this. For the moment, I'm going to store h of 2 as alpha a. So why am I doing that? Just to save myself the trouble of having to bring that value back in. Second, we need to calculate h prime of 2. So for that, I'm going to do math 8. So when I use x, we're using alpha calc, or alpha trace y1, and we're going to do it specifically at x equals 2. Pressing enter gives us, this is our slope, 1.619935998, and I'm going to store that one as alpha b. So for the moment, weird as that is, we're letting h of 2 equal a and h prime of 2 equal b. That means this is going to be the equivalent of 44a plus 3b. In our graphing calculator, we can ask it to compute that for us. 44 alpha a plus 3 alpha b is going to give us the value of negative 13.177, or negative 13.176. Get all the, oops, wrong thing. Gets us 868, and then I'll dot it. So we've now found our p of 2. We've found our slope. So now we can write out our tangent line equation. Our tangent, actually I'll write it down here. I think I may have actually forgotten this in the written solution. I'll have to look. Our tangent is going to be y minus a negative 1.22. Okay, so be careful. This is 2297. So that's going to be 230 is equal to our slope, negative 13.177 x minus 2. So there is our tangent line. Quite an adventure to get there. Again, challenging just because you're juggling so many pieces. But again, it was familiar stuff, product rule and chain rule, as well as using a graphing calculator to pull in values. And then, of course, I used some clever storing value techniques to make sure that I didn't lose any accuracy as I ran my way through. So voila, there is 11A. Next, we have 11B. 11B is the calm before the storm. 11B is the, it's the nice part of the problem. We are asked to approximate G double prime of 4. So what I'll remind you is if you want to approximate G prime of C, you can do that using the difference quotient, G of B minus G of A over B minus A. The problem is here we're not using G double prime. Or here we're not using G prime but G double prime. So if we want to do G double prime of C, we need to use not G but G prime. So same setup, we're using a difference quotient or an average rate of change to approximate the instantaneous or derivative, but we're just going to have to use the derivative. So in our case, we're looking for an interval that has 4 in the middle. Looking at my table, I see very clearly that 3 and 5 both do. So for our purposes, I'm going to say that G prime of 4 is approximately equal to G prime of 5 minus G prime of 3 all over 5 minus 3. And simplifying that a little bit, G prime of 5 it says is 11, G prime of 3 is 4, all that's over 2. We're going to get that G prime of double prime, of 4 is approximately 7 over 2. And again, we're just using the average rate of change, so that's one thing to keep in mind. The average rate of change, I wish there was an abbreviation or symbol for that. The average rate of change is approximately equal to the instantaneous rate of change. So voila, 11B is finished. So here we are. This brings us to 11C. In my opinion, 11C is one of the hardest questions I have ever put on a problem set in any course at any time. And there's just so many ways to mess it up. There's just so much stuff happening in 11C, and you're having to do so many different things. So if you're looking for something to really test your ability to know how to manufacture differentiability, if you can get this right, you have nailed this. This is like a plus kind of question. So I'm going to work through it the same way I did last night after I wrote it. It does exactly what I wanted it to, but boy did it make me break a sweat when I was doing it. So here it is. So first, it starts by defining b of x as the function h of x when x is negative, a line mx plus b when x is between 0 and 3, and g of x when x is greater than or equal to 3. So we've got the table function, we've got the calculator function, and we've got the line mx plus b. And we're supposed to find the values, of course, of m and b such that b is differentiable. So if you'll recall, to get a function to be differentiable, we need b to be both continuous and we need b prime to be continuous. In other words, we need it to be both continuous and have matching non-sharp turn slopes. So what I typically do is I try to prolong as long as possible any work with b prime just because that takes a little bit more work to get to. So what I'm going to do in this problem is I'm going to start by checking for the continuity of b at both, at both boundary points. It literally starts with the b. So I'm going to look at the two boundaries, check continuity, then I'll go to the boundaries for b prime and check continuity of the derivative. So in organizing my work, where I'm going to start is I'm going to start by asking myself, is b continuous? And of course, there's lots of different places to consider, but specifically we're interested in the two boundaries of 0 and 3. So I'm going to start with at x equals 0. That's going to be my focal point first. So is b continuous at x equals 0? Well, as we've said many times before, when we're checking for differentiability or continuity, it typically boils down to just looking at the limits themselves. Does the limit exist? Because what's tough about this is we're trying to match up two different functions at the same place. So in here, if b is continuous at x equals 0, we're going to need the limit as x approaches 0 from the left side of b of x to equal the limit as x approaches 0 from the right side of b of x. Right? I mean, that's fair. It's the same thing as always. Looking at our function, that's going to mean that we need h of 0 to be equal to m times 0 plus b. Ooh, oh, this is awesome. I can't believe this, guys. Look at this. H of 0 is equal to 0 plus b. So, oh, heck yes. That means h of 0 equals b. Well, looking up there is h of x. So if we want to know what h of 0 is, that's going to be 2 to the negative 0. Sorry, ln. Forgot the ln. 2 to the negative 0 plus pi minus 3 sine of 0. FYI, that's just 1 plus pi minus 0. We end up with that being equal to ln of 1 plus pi. So without further ado, we're one step into the problem, and we got b is the ln of pi plus 1. So, look at that. People are telling me this is going to be hard. Maybe I just forgot what happened. Excuse me. So that was the boundary at x equals 0. It was a pretty fruitful negotiation to pull out that much information. But of course, we have a second one to consider. In particular, we're interested in what's happening at x equals 3. So of course, if b is continuous at x equals 3, that implies that the limit as x approaches 3 from the left side of b of x is going to be equal to the limit as x approaches 3 from the right side of b of x. Again, should make sense. We want to make sure they match up. Otherwise, if it's not continuous, we have a discontinuity there. That'd be bad. So in looking here, looking on the left side, that's going to be the line. So it'll be m times 3 plus b. On the other side, we're going to have g of 3. Well, looking at our table, g of 3 is equal to negative 2. So we have 3m plus b equals negative 2. But we already found b. Just look at that. So in other words, we have 3m plus the natural log of pi plus 1 is equal to negative 2. And if we solve this around, we'll get that m equals negative 2 minus the ln of pi plus 1 all over 3. Let's make that right. So in other words, that's our m value. And you know what? I'll approximate this value really fast before we go forward. So, and I should have approximated the other one as well, just for the record. So getting these values in, ln of pi plus 1. So the value over here is 1.421. I'm just abbreviating it or truncating it. On the other one, we want to do negative 2. Do this one calculation. Math, fraction. We're going to do negative 2 minus the ln of pi plus 1. And it's all divided by, 3. Gives us that m is negative 1.140. Yep. So I do equal negative 1.140. So dot dot dot. So hey, at this point you'd go, hey, look at that. We were supposed to find M and B. We found them already. We're done. That's the whole problem. Box your answer, box your answer. You feel really good about yourself, don't you? Here's the problem though. What we've done is we've found values that make our function continuous. The question still remains though, does this continuous function actually meet all requirements of differentiability? In other words, does this make b prime continuous? Because if it doesn't make b prime continuous, or excuse me, if it doesn't make b prime continuous at either of the boundaries, this actually didn't work, and we will find that there's no solution. So let's do one more check. And you know what, for simplicity, let's check the right endpoint. So our next question, as we've asked before, is to ask, is b prime continuous? So in other words, we're looking to make sure that we have a smooth curve. And I'm going to start with x equals 3. So at x equals 3, if b prime is continuous, of course, we'll need to consider the limit as x approaches 3 from the left side of b prime. And we need it to be equal to the limit as x approaches 3 from the right side of b prime. So of course, we haven't found b prime yet. So let's do a quick calculation up here. B prime, actually I'll do it on the side. I guess I got enough room here. B prime of x, in our case, looking at simplicity here, we're going to have h prime of x when x is negative. We're going to have the derivative of mx plus b, since its a line is just the slope, so m when x is between 0 and 3. And then we're going to have g prime of x when x is greater than 3. So not a hard derivative to calculate, actually, so that's kind of nice. So from here, we want to evaluate these pieces. So if we want the limit as x approaches 3 from the left side, that's going to come from the line. So that's just going to be equal to m. And then on the right side, we're going to have g prime of 3. So in other words, what this tells us is this should just confirm what we had before. G prime of 3 is 4. So that says that m equals 4. It says m equals 4, but based on the work we did earlier, this tells us that negative 1.140 dot 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 equals 4. I feel like someone should let Bank of America know that, because I'm pretty sure negative 1.140 is not the same as 4. And in fact, this is absolutely false. And what that tells us is that we don't need to do any more work. There are no such values of m and b. Basically, what this is telling us is that if we were to... Did I use capital B in a function named b? I'm annoying. Whatever. What this basically tells us is that depending on which path we take, either checking b's continuity or b prime's continuity, we get different requirements. And unfortunately, what that means is this is actually impossible. More than that, this function is literally impossible to end up with a single line. It happens that, I don't have the graph handy, but I'm pretty sure the graph looks something like this. I don't remember what it was. It was something like that. And then there was the G, which seemed to be sort of like that. There's no way to connect a line and end up with it perfectly smooth on both boundaries. So in fact, it's impossible based on what's there. I guess it's just impossible to end up with that. We can't have the slopes match the same way on both sides. So in other words, this does not actually work. There are no such values. But the difficult thing, the reason this becomes so difficult is not only is it cumbersome to work your way through and involving 3 different types of things, the other reason is that you get apparent answers after doing 2 steps of work. And even here, it would have been even easier. You would have gotten m equals 4 if you'd done that first. But unfortunately, there are no values. This one has no real solution. So therefore, it's pretty tricky. And again, this is not a test-worthy question. This is a great question. But this isn't something that's going to be on a test. It's just a great question to really probe whether or not you've got this concept or not. And there it is, 11C in all its glory. Alrighty, this brings us to the final question of the assignment, mercifully, because I swear I'm into like hour 3 of working on this one. In question 11D, using the same numerically presented function and that calculator needy question function h of x, we are told, let c of x equal h of g of x. So classic chain rule, thank you. If c prime of negative 1 equals 2 pi, find the value of k. So set aside the little grammar issue right there. I'm going to have to work on that a little bit as well. Got some stuff to hit. So for the moment, though, we can go ahead and attack this. So we're interested in C prime negative 1. We're given C, so I want to figure out what C prime of x is equal to. So starting off, again, we've come this far. I might as well be as careful as possible. So I'm going to let a function, we'll consider C. We'll have C of u and u equal, or sorry, C of u is going to be h of u, and u is going to be g of x. When you differentiate, it should be fine. When you differentiate, we're going to get C prime of u is equal to h prime of u, and u prime is equal to g prime of x. This is all crazy. This is classic chain rule. I'm just being super careful. This will then give us our final derivative C prime of x as h prime of u, but u is g of x, so I'll just shove it in, times u prime, which is g prime of x. So in other words, to get us started, C prime of x is equal to h prime of g of x times g prime of x. So far so good. Next piece, we want to calculate C prime of negative 1. So let's plug in negative 1. H prime of g of negative 1 times g prime of negative 1. So now we're going to have to read out of the table a little bit, switch colors for that purpose. So in the table, g of negative 1 is 5, heck yeah. It's going to be equal to h prime of 5. G prime negative 1 is g prime negative 1 is k, so we have that. And then last but not least, they tell us C prime of negative 1 is 2 pi, which means this expression is actually equal to 2 pi. We want to find the value of k, so in order to do that, I simply need to divide both sides by h prime of 5. So in other words, k is going to be equal to 2 pi over h prime of 5. But of course, we've said this before, we don't have the ability to differentiate h by hand just yet. So to help me out of this jam, I'm going to go in. Let's make sure first and foremost, h is still y1. I'm going to ask for math 8, or the derivative with respect to x, of h of x at x equals 5. So this will give us h prime of 5. So that's negative 0.144248. So 2 pi over negative 0.14428 stuff. And when I divide those two things to get by one another, when I divide appropriately, we're going to get 2 pi divided by our answer. So I'm going to go second enter. Oh, that didn't work. I did entry, excuse me. 2 pi divided by the answer. I cannot see. You guys haven't figured this out just yet. I'm unable to see. Oh, here's what I'm going to do. 2 pi divided by that. I get my answer of negative 43.558. So setting aside the fact that finally things are too small for me to see with my fake glasses, we have our final k value. And with that said, we have finally ended this assignment. As I said, this is a challenging assignment. I covered a few extra problems and included a couple really tough wrinkles on there. Hopefully these videos have been informative and helpful in helping you understand and command advanced differentiation. Without further ado though, have a great night.